I'm Rusdi Shanti Chalaya, and in this video lecture, I am going to take a type of A to D converter which includes single slope and dual slope converter. In this lecture, I am going to discuss the working principle of A to D converters using op-amp, which includes single slope and dual slope A to D converter. Single slope A to D converter converts an unknown analog input voltage into digital value by measuring the time it takes for a reference ramp voltage to match with the input voltage. The count represents the input value. The single slope A to D block description is given in this slide. The core blocks of the single slope A to D are ramp generator, comparator, counter, clock signal, and the control logic. It converts an analog voltage into a digital value by measuring how long it takes for the linearly ramped reference voltage, which is similar to sawtooth waveform, matches the input voltage. The conversion process takes place in three main stages. The system's binary counter and the ramp generator are both reset to 0. The ramp generator outputs a linearly increasing reference voltage, which is nothing but a simple integrator. At the same time, the digital timer counter starts counting the clock pulses. A comparator continuously compares the ramping voltage against the analog input voltage. While the ramp voltage is lower than the input voltage, the counter continues to count. The exact moment the ramp voltage reaches the same level as the input voltage, the comparator switches the states. This triggers the switch to stop the counter. The final value displayed on the counter is the equivalent digital output for the input analog voltage. Because the ramp increases at a constant speed, the total count is directly proportional to the voltage of the analog signal given. The formula is given as capital T is equal to V in into R into C divided by V reference. The conversion time capital T is the input voltage by the integrator constant, where T is the time taken to reach the parity, V in is the unknown analog input voltage, R is the resistor capacitor value of the integrator. V reference is the reference voltage. It converts an analog input voltage to digital value by measuring the time it takes for a known reference ramp voltage to match the input voltage. The ramp starts from 0. The counter counts the number of clock pulses until the ramp voltage equals the input voltage. The advantages and disadvantages of the single slope A to D converters are discussed here. The advantage is that it's highly accurate, very simple circuit composition and low noise sensitivity, and it is low cost. Disadvantage is that it is slower conversion speed compared to flash type A to D, and vulnerability to clock and temperature drift is allowed. So for a deeper dive into the circuit components, the op-amp that makes this possible to do the A to D conversion in a easy way. The slow conversion speed and accuracy depends on the ramp linearity. Now we discuss the principle of operation of next type of A to D converter in dual slope concept. The dual slope A to D converter converts the analog input into an digital value by utilizing the distinct integration ramp over time. It consists of 5 primary hardware components. The input voltage is integrated for a fixed period, then deintegrated using the reference voltage. Integrates the input voltage, then applies analog switch which alternates between unknown analog input voltage Vin and known reference voltage minus V reference. Then next block is the integrator which the op-amp circuit featuring a resistor and capacitor produces linear voltage ramp. Then next block is the comparator compares the integrator output voltage V out against the ground reference voltage V to a signal when the ramp returns 0. Manages the input switch position, resets the counter and reads the state signal. The binary counter measures the time interval by counting the internal clock pulse. Thus, the time taken for the input reference voltage and the analog voltage is calculated and the equivalent digital output is displayed using the counter and display. It works in two-phase process. In phase 1, the upslope integration phase, the switch connects the analog input voltage Vin to the integrator. Over fixed period time T1, the integrator produces a linearly ramping voltage. The peak voltage reached at the end of this is directly proportional to the magnitude of V in. The equation for this slope is V out is equal to minus 1 by the integral of V input. Then next phase is downslope de-integration phase. The switch disconnects V in and connects the known reference voltage minus V run of the opposite polarity to the integrator. Because the reference has an opposite polarity, the integrator output ramps downward towards 0 volt. The counter starts counting clock pulses the moment the downslope begins. When the integrator output hits exactly 0 volt, the comparator stops the counter. The time this takes is known as T2. Because the volt second inputs are equal, the unknown input voltage V in is calculated using the formula V in is equal to V reference into T2 by T1. Since T1 is and V reference are constant, the unknown voltage V in is entirely dependent on T2, that is the time measurable factor. The counter's final value is the resulting digital output. The advantage of this method, dual slope, has excellent noise immunity. The integration naturally cancels out the high frequency noise and AC line interference and high measurement resolution. The disadvantage is that it has lower conversion speed because it relies on two time-based integrating phases. The common applications of this A to D converters are universally used in digital multimeters and precision panel meters because of their high precision and ability to measure average voltages. Thus, the use of A2D has declined to be wonderful resource for another accurate and consistent ABC, which find wide usage in design of digital multimeter. This lecture covers integration, de-integration phrases, timing relationship, and the key formula to calculate the input voltage. Thank